So, good evening, everyone. Welcome to the week 7 of this tutorial session on the course of Principles of Modern CDMA, MIMO, OFDM Wireless Communication. So, today we'll see the basics of MIMO system and we'll solve some of the problems based on that. So, yesterday what we have seen, like the basic block diagram of the MIMO system. So, basically there are there are T transmitter antenna at the base station side and R receiver antenna. Let's suppose these are the T transmit antenna and R receive antenna. So symbols are transmitted from transmitter to receiver through. So the transmit symbols are represented as X bar. So basically today we will see uh, the the equation for the zero forcing decoder, the derivation of that, and then we will solve some of the question on that. So the transmit symbol X bar, and that is like the T transmit symbol X bar vector represents the T transmit symbol, and Y bar is the received symbol vector. So that is Y1 to YR. So this is the received symbol vector Y bar. So this is our MIMO channel, and the transmit symbol is X1 to XT, and the receive symbol vector is Y1 to YR. So basically our channel will be R cross T. This is the dimension of our channel. So this is the dimension of the channel vector. Okay. So H is represented as H11, H12, and H1T. So the number of columns will be T here. As you can see, this is the number of columns, and R is the number of rows. So here we can write again H21, H22, H2T. Similarly, HR1, HR2 and HRT. So here the dimension of this channel vector is R cross T dimension. So when we write the complete received symbol vector expression, so here y bar is equal to hx bar plus n bar. So this we can also represent as y1, y2 to yr. There are received symbol vector, and this is our channel matrix. And the dimension is r cross t. The dimension for this received symbol vector is r cross 1. Now next is the transmit symbol vector, that is x1, x2 to xt. So this is t cross 1. Now again there will be noise added at the receiver. So this will be n1, n2 and r. Again this is our r cross 1 noise vector. So the received symbol can be represented as y1 is equal to h11 x1 plus h12 x2 plus dot 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 h1t xt plus n1. Okay. So basically this y is equal to hx, and x1 and x2 and xt are the unknowns. And how many equations are there? There are r equations. So t unknowns are there and r equation are there. Okay. So when r is equal to t, in that case H will be our square matrix. But when r is not equal to t, H is not a square matrix. So what is the significance of this square matrix? Here easily the H inverse exists. Okay. So like if y is equal to hx, then we can write x hat is equal to H inverse y hat. So, so when r is equal to t, then number of receive antennas uh, are equal. So therefore inverse exists. But when the r is greater than t, so in that case, the number of receive antennas are greater than the transmit antenna, and the inverse does not exist. Okay. So now let's find the let's take the error function. Error function is the estimated value and the so this error is given as y minus hx mod of a square. So this is known as the least squared error function. And we'll also see if h inverse does not exist, then in the next lecture maybe we will see similar value decomposition for this, or maybe in today's lecture, mostly next lecture. So now this is the least square estimator. So here fx is equal to y minus hx square. So this we can write as y minus hx transpose y minus hx. Okay, because x transpose x is mod of x square. So here, after multiplication, we will get y transpose minus x transpose h transpose multiplied with y minus hx. Also, to minimize, what we can do, uh, we will equate the derivative to 0. So now y transpose y minus x transpose h transpose y minus y transpose hx plus x transpose h transpose h into x. So these are the four terms after multiplying. So this we can write y transpose y minus these two terms we can write as 2 of x transpose h transpose y plus xt ht hx. So now to minimize the error, we have to do derivative equal to 0. So this is already derived in class. So we will get the estimated x hat is equal to h Hermitian h inverse h Hermitian y. Okay. So this is the zero forcing receiver, or known as zero forcing decoder, so also known as FZF. If it is non-complex term, then we can write H transpose H inverse into H transpose. But when there is a complex scenario, in that we have to write H Hermitian. So now we will see properties of the zero forcing receiver matrix. So properties of the zero forcing receiver matrix. So that is FZF. First of all, what is FZF? As derived in the classroom, we will get this as H Hermitian H inverse H Hermitian. Okay. So now let's multiply it with a vector H on both the sides. So after that, we will get H. This is the first one. Now here we can write H Hermitian H. So here you can see this is, let's suppose this is our A. So what is this? A of inverse. So this will become IT. Okay. Now, but only this can happen when we do the post multiplication of H. If we do HFZB, then we will get H of H Hermitian H inverse. So this is not equal to identity matrix. Okay. So the zero forcing decoding vector, that is given as, so basically we have to remember this formula. So this is very important. The ZF, that is the zero forcing receiver vector. So that is given as H Hermitian H whole inverse into H Hermitian. Okay. And also let's expand this. What we will get? So when we like break this bracket, then you will get H inverse, H Hermitian inverse, and this term is H Hermitian. Okay. So now this will become again identity matrix. So this will become H inverse. Okay. So basically the zero forcing decoding vector is the inverse of this channel vector. Okay. So what we can write from this statement, FZF is the pseudo inverse of channel matrix. And now we will solve some of the questions based on this week whatever is taught. So the first question is based on the LMOT coded wireless system. So here x1 the the transmit symbol vector is given as 2 plus j and x2 is 3 minus j. So the symbol vector transmitted during the second time instant in this system. So the symbol vector transmitted during the second time instant, just give me a minute. Second time instant it is given as minus of x2 conjugate x1 conjugate. So x2 conjugate will be 3 plus j and minus will be minus 3 minus j and x1 conjugate will be 2 minus j. So the option B is correct. Yes, somebody commented also. So this option is correct. It's just a simple question based on the formula which is taught in the class. Now coming to the question number 2. Consider the MIMO channel matrix H is given as 1 minus 1, 2, 2, minus 1, 3. So what is the dimension of this? This is 3 cross 2. So now from here you will have to say how many, if it is asked how many receive antenna and transmit antenna is there. So it is H R cross T. So here R is our 3 and T is 2. So just for the dimension I am saying, so there will be 3 receive antenna and 2 transmit antenna in this case. Now in this question it is asking the corresponding zero forcing receiver matrix is. So the zero forcing receiver matrix is given as, it is the real values, all terms are having the real value, so we can write H transpose instead of H Hermitian. So H transpose H whole inverse into H transpose. So now what is our H transpose? This is given as 1, 2, minus 1, minus 1, 2, 3. Okay. And H transpose H will be so this will be 2 cross 3, 3 cross 2. This is 2 cross 2 matrix. 1 plus 4, 5 plus 1, 6. 0 minus 1 plus 4 minus 3. 0 1 plus 4 5 plus 9 4. Okay. Now what is H transpose H inverse? It is a simple 2 cross 2 matrix, so we can directly find the determinant and divide it by the matrix 1 by 84, and just reverse the diagonal element here. So we will get this. So this will be 1 by 6, 0, 0, 1 by 4. Okay. So now H transpose H inverse multiplied with H transpose. So that will be 1 by 6, 0, 0, 1 by 14 multiplied with H transpose. That is 1, 2, minus 1, minus 1, 2, 3. So this is equal to 1 by 6, 1 by 3, and minus 1 by 6. Minus 1 by 14, 1 by 7, 3 by 14. So this is the zero forcing vector receiver here. So the correct option is option number D. And also for a bit error rate, just I want to give the equation before solving the question. Bit error rate for BPSK with zero forcing receiver is given as 2L minus 1, choose L, 1 by 2 SNR to the power of L. And here the value of L is equal to R minus T plus 1. Okay. So R is the number of receive antenna, T is the number of transmit antenna, and 1 we can. So again this we can write 2 R minus T plus 1 minus 1 C R minus T plus 1 1 by 2 SNR to the power of R minus T plus 1. So this is our formula for the bit error rate for BPSK with zero forcing receiver. Now let's take one example for this question. Consider a 3 cross 2 MIMO system where SNR is equal to 25 dB and the decoder is ZF receiver. We have to find the bit error rate. Okay. So here you can see it is a 3 cross 2 system. Okay, so R is equal to 3 and T is equal to 2. What is our L? L is R minus T plus 1, that is equal to 3 minus 2 plus 1. So that is 2. So the average bit error rate is equal to LC, like the equation we can see 2L minus 1 CL. Here 2L minus 1 CL 1 by 2 SNR to the power of L. So the value of L is 2 here. So 4 minus 1, 3 C2 1 by 2 SNR to the power of 2. And SNR is given as 25 dB. So 10 log 10 SNR is equal to 25. So SNR is equal to 10 to the power of 2.5. So this value will come somewhat approximately 316.2. Okay. So again, the BER is given as 3 sub 2. So 3 factorial divided by 2 factorial into the 3 minus 2, 1 rand. Okay. And 1 by 2 square. So this is 1 by 4 into 1 by SNR. SNR is 316.22 to the power of 2. Okay. Or we can write here 10 to the power of 2.5. So it will be easy. So this will be 3 by 4 into 1 by 10 to the power of 5. Okay. So bit error rate is equal to 0.75 into 10 to the power of minus 5. So in this way, we can find the bit error rate for MIMO system with zero forcing receiver with BPSK. So now we will move on to the next question. So this is again similar kind of question. Consider a 5 cross 3 MIMO system. So 5 cross 3 means R is equal to 5, T is equal to 3. Okay. So what is the value of L? R minus T plus 1. So this will be 2 plus 1, 3. With a zero forcing receiver, the SNR in dB is required to achieve a given bit error rate is. So the bit error rate formula is given as 2L minus 1 CL 1 by 2 SNR to the power of L. So we have to find the SNR. So this value we have to find. So we will solve in such a way that SNR will come on the left hand side and all other things comes on the right hand side. Okay, we have to find in terms of bit error rate because in this question the bit error rate is not given. If it is given, then we can substitute the value and find the answer. So this is equal to 6 minus 1, 5C3 1 by 2 SNR to the power of 3. 20 by 2. So this is 10 into 1 by 8 into 1 by SNR cube. This will become 5 by 4 SNR cube. So here SNR cube will be 5 by 4 into bit error rate. Okay. So imply that SNR is given as 5 by 4 bit error rate to the power of 1 by 3. Now in this question it is asking dB, SNR in dB. So for dB we can do 10 log 10 SNR. So SNR in dB is equal to 10 log 10 SNR. So 10 log to the base 10 10 by 3. So some bit error rate is, let's suppose, given like 7 into 10 to the power of minus 5. Then substitute and we can get our SNR in dB. Okay. So this is very simple way to find. Yeah. So option is 10 by 3 log 10 5 by 4 BER. So option D is the correct answer for this question. Now consider SNR is equal to 30 dB in 1 cross 3 multiple input single output. Here receiver is 1 and transmitter is 3. So there is multiple input because there is 3 transmitter and 1 receiver. So input is multiple and output is YR. So YR is single. This is Y1 only. R is equal to 1. Okay. So the bit error rate with transmit beam forming is given as. So first of all, SNR is given 30 dB. So let's convert this SNR in normal units. So SNR is equal to 10 to the power of 3. So let it be, that is 1000. Now, this is a 1 cross 3 MISO system. As we have already seen, 3 transmitter and 1 receiver. Here you can see 3 transmitter and 1 receiver. So in this case, in 1 cross 3 MISO system, so our L is equal to R minus T plus 1. So R is so basically like in this case, uh, so in this case, R minus T plus 1 it is given. So R is here less than T. So in this case, we can do mod of this. So here we'll get 3 minus. Now basically, it is a multiple MISO system. In such kind of system, where like if number of like receiver is less than the transmitter, then we take the maximum value, that is the transmitter T is equal to 3. So in such case, L is equal to 3 here. Okay. So bit error rate is given as 2L minus 1 CL 1 by 2 SNR to the power of L. So 3 when you substitute, so 5C3 1 by 2 10 to the power of 3 to the power of 3. So again it will be 20 by 2. 10 by 8 into 1 by 10 to the power of 6. Like it is a MISO system. So in this case, like whenever we have like L is equal to R minus T plus 1. So when R is greater than T, so in that case we can take this formula, okay? But in the case where number of transmitters are more, here you can see there are 3 transmitters. So in this case we will take L is equal to 3. As it is a multiple input single output system, so we can consider as a like L is equal to here 3, like when R is less than T, then we will choose the value of T, that is the number of transmit antenna. So now again we will get 1 by 8 sorry, it will be 3 into 3, that is 9. So this will be 10 to the power of 3 into 3, which is 9. So this will become 10 to the power of 8. or we can let it be the simple one. Don't cut. So better do this 5, 4, and so it will become 5 by 4 into 10 to the power of minus 9. So this is 1.25 into 10 to the power of minus 9. So option D is the correct answer for this question. Now coming to the question number 5. So in this question it is asking, consider total transmit power. Total transmit power P is 9 dB. So this is total transmit power. Okay. Sigma square is equal to 0 dB, and it is a 2 cross 2 MIMO channel with singular values, that is sigma 1 is equal to 1 by 2 and sigma 2 is equal to 1 by 2 root. Okay. So now the optimal power values for the two singular modes are, okay. So like for two singular modes, what will be the optimal power value? So we know the equation P1 is equal to, as taught in the class, that is 1 by lambda minus sigma square by sigma 1 square. Similarly, P2 is equal to 1 by lambda minus sigma square by sigma 2 square. So the same equation we will use here. The total power is 9 dB, so 10 log 10 PT, that's the total power as PT, is equal to 9. So PT is equal to 10 to the power of 0.9. So this will be around 8. Now sigma square is equal to 0 dB. So 10 log 10 sigma square is equal to 0. So sigma square is equal to 10 to the power of 0. So this is 1. Now P1 is equal to 1 by lambda minus sigma square, that is 1 by sigma 1 square, 1 by 4. Okay. Similarly, P2 is equal to 1 by lambda minus 1 by sigma 2 square, that is 1 by 4, it will be 1 by 2 root 2 square. So it will be equal to 1 by 4 into 2, 8. Now the total power is equal to P1 plus P2. So this is equal to 1 by lambda minus 4 plus 1 by lambda minus 8. So that is equal to 2 by lambda minus 12, and this is equal to 8 because PT is equal to 8. 2 by lambda is equal to 20, 1 by 10. So now our P1 is equal to 1 by lambda minus 4. So 1 by 10 is equal to 10 minus 4, that is equal to 6. P2 is equal to 1 by lambda minus 8, that is 10 minus 8, 2. Okay. So P1 comma P2 is 6 comma 2. So option D is the correct answer for this question. So now consider a 1 cross 2 MISO system, that is a 1 receive antenna, 2 transmit antenna with channel H is equal to H1, H2, total power P and noise variance sigma square. The output SNR for each symbol after combining in a multi-coded system is. So the SNR output as taught in the classroom, it is half H squared P by sigma square. So it is option number D. We'll solve one question on this. So let's take an example. Consider 1 cross 2 MISO system. Here our H1 is 2 plus J and H2 is 1 minus 2J. Okay. What is the optimal so what is the optimal transmit beam forming if CSI channel state information is available at transmitter? So again, if the channel state information is available at transmitter, in that case, like we can use the allomotive coding, and here x bar is given as x bar is given as H1 transpose H2 transpose, okay, multiplied with norm of H into X, and Y is given as 2 plus J 1 minus 2J. This is our H1 H2 into X1 X2 plus omega, okay, because Y is equal to Hx plus omega. Omega is here noise vector, and this is our X. So in this case, like we have to find the SNR. So H1 is 2 plus J and H2 is 1 minus 2J. The norm of H will be 4 plus 1 plus 1 plus 4. That is equal to square root of 10. And what is our X bar? That is given as H1 conjugate 2 minus J, 1 plus 2J, 1 by square root of 10. And what is our vector X? Here we can write X. So what is Y? Y in this case will be Hx plus omega. So H is 2 plus J, 1 minus 2J. So this is our H vector. And now X vector is 2 minus J, 1 plus 2J, 1 by square root of 10 into X plus omega. This is our X vector and this is our noise vector. So now when we do Y is equal to 2 plus J, 2 minus J, it is equal to 4 minus, minus 1 square, so it will be 5. And again 5 plus 5, 10. So 10 by root 10x plus omega. So this is equal to root 10x plus omega. Now SNR is equal to 10 into power of this symbol P divided by the power of noise sigma square. So this is 10P by sigma square. Okay. So allomotive code is the orthogonal space-time block code. Yes, this is correct. So option A is correct in this question. Now again, there are a few more theoretical questions. Orthogonal frequency division multiplexing, OFDM is a wireless system, aims to overcome inter-symbol interference. Okay, OFDM is used to reduce the inter-symbol interference, ISI. Coming to question number 9, consider a symbol x1 is equal to 1 minus 2j and x2 is equal to 2 plus 3. For an allomotive coded 1 cross 2 wireless system, the symbol vector transmitted using second time instant is. So, the symbol vector, I think this is similar question what we have done in the first one. Transmitted during second time instant is minus x2 conjugate x1 conjugate. Then minus 2 plus 3j, 1 plus 2j. So option number C is the correct answer. The next question is also similar only. Just a minute. Consider a 4 cross 3 MIMO system with a zero forcing receiver. So R is equal to 4 and T is equal to 3. The DBS and R required for given bit error rate. This is similar question what we have done. L is equal to R minus T plus 1. So it will be 2. Bit error rate is equal to 2L minus 1 CL 1 by 2 SNR to the power of L. Now substitute L is equal to 2. We will get 3C2 1 by 2 into SNR to the power of L. So bit error rate is equal to 3 by L is equal to 2 here. So 3 by 4 1 by SNR squared. So SNR is equal to 3 by 4 bit error rate the whole square root. So SNR in dB is equal to 10 log 10 3 by 4 bit error rate to the power of half. Because square root we can write it as half. It will become 5 log 10 3 by 4 BER. So option number C is the correct answer for this question. We will see just a simple concept as some revision we will do from the previous concepts also. So let's see the BER of BPSK. Okay, just we'll do revision what we have studied in the first lecture. So here we know YK is given as XK plus NK. So X is the transmit symbol vector, N is the noise vector. Now XK is given as 1, like X is decoded as 1 if YK is greater than 0, and it is decoded as 0, XDK is equal to 0 if YK is less than 0. Okay, so this means the transmitted symbol power is transmitted symbol is root P, and in this transmitted symbol is minus root P. So let's suppose transmitted symbol is equal to 0. So what is transmitted? Square root of P. So YK is equal to minus root P plus NK. Now for error to occur, sorry. Yk should be greater than 0 at the receiver, then only it will decode as a plus 1, that is square root of p. So minus root p plus nk should be greater than 0, and this also makes sense. Like when noise is greater than the symbol, okay, uh, the power of noise is greater than the symbol power, then the probability of error will occur. That is nk is greater than square root of p. So probability of nk greater than square root of p is equal to q function of square root of p by sigma square. That is a q function of square root of SNR. Okay, why? Because SNR is equal to p by sigma square. So bit error rate is given as q function of square root of SNR, and also the q function of SNR, like square root of SNR, this is less than equal to half e to the power of minus SNR by 2. So these are the approximate equation what we have studied. So just I am writing for the revision. Okay, and how we find SNR in dB? That is equal to 10 log 10 the normal SNR, that is p by sigma square. Okay, so let's solve one example and we will also see the bit error rate of BPSK over a relay channel. What is the bit error rate of BPSK communication system over an AWGN communication channel at SNR in dB is given as 10 dB. So what will be the SNR? That is 10 to the power of 1. So now the bit error rate is given as Q of square root of SNR. That is Q of square root of 10. So this value is somewhere near 7.8 into 10 to the power of minus 4. And also one more thing we have studied, that bit error rate of BPSK in relay fading is given as Q table you can find on internet or in some of the book also it is given, but it will be available on internet. You can search Q function for communication system. So bit error rate of relay is given as half 1 minus square root of SNR. This we have already studied, 2 plus SNR. Okay. And what is the approximate equation of this? Let's suppose SNR is 10 here. So what will be the bit error rate in relay fading channel? Half 1 minus square root of 10 by 12. So again, just give me time. we have 1 minus, this is 0 point around 9. So we will get 0.1 by 2. That is 0.5 into 10 to the power of minus 1. So somewhere nearly equal to 5 into 10 to the power of minus 2. Okay. And also we can approximate bit error rate in Rayleigh-Frederick channel is equal to half 1 minus SNR by 2 plus SNR. So half 1 minus, we can write it as 1 by square root of 1 plus 2 by SNR, because this SNR will go above and this will be SNR plus 2. Okay, we can write like this. So this will be nearly equal to half 1 minus, this term is 1 minus half into 2 by SNR. In the Taylor expression, Taylor expansion, we can do this. So this will become 1 minus 1 will be 0 and this will be plus of SNR. So this will be equal to 1 by 2 SNR. So this is for the larger value of SNR. Okay, so these things we have studied in the first lecture. So today we will stop here. In the next week we will solve some question and also we will solve some of the previous week formulas we will see, and we can solve some question also based on that. So thank you everyone for attending today's lecture. So we'll end the class here. Thank you.